filling of orbitals in an atom. Now here we have got to learn three important principles. The first one is Aufbau principle. Aufbau principle states that in the ground state of an atom, the orbitals are filled in order of increasing energies. And we already saw the increasing order of energies in multi-electron atom. The order in multi-electron atom is 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d. Now there is another method to find. So till 3d you have to learn by heart. Now there is another method with the help of Aufbau principle. We can find the order of increasing energies of orbitals. It is this way. Write 1s, 2s, 2p, 3s, 3p, 3d, then 4s, 4p, 4p, 4f, 5s, 5p, 5d, 5f. So you can see we will start from here. 1s orbital less than 2s orbital less than 2p less than 3s less than 3p less than 4s less than 3d less than 4p less than 5s less than 4d less than 5p. Here we have 6s. So it goes like this. But you have to learn till 3d by heart. Okay, so this is Aufbau principle, that is in the ground state of the atom, the orbitals are filled in increasing order of their energies. Now the second principle is Pauli's exclusion principle. Pauli exclusion principle. Now, what is Pauli exclusion principle? It states that no two electron in an atom can have the same set of 4 quantum numbers. No two electron in an atom can have the same set of all 4 quantum numbers. They will have same n value, L and m value, but their spin quantum number s will be different. For example, you take 3s orbital, and if there are 2 electrons present in 3s orbital, the n value for the first electron, n value will be equal to 3, L is equal to 0 because it is s sub shell, and m is also equal to 0. Now for second electron, n is equal to 3, L is equal to 0 and m is equal to 0. But so 3 quantum numbers are same, but the fourth one spin will be different. For the first electron, if the spin is plus half, then for the second electron spin will be minus half. So this is Pauli exclusion principle. No two electron in an atom can have the same set of all 4 quantum numbers. Now the third rule is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Yes. This rule states that pairing of electron in an orbital belonging to the same subshell does not take place until each orbital belonging to that subshell has got 1 electron each. That is, it is singly occupied. That means we have p orbital, 3 p orbitals, px, py and pz. So 3 p orbitals, and suppose we have 4 electrons to be added to p orbital, then that addition of that electron takes place in such a way that first each p orbital gets singly occupied. So one electron will first go to px, second electron goes to py, third electron goes to pz. Now only after each p orbital gets singly occupied, pairing of electron take place. So the fourth electron will again pair up in px orbital. Okay, and the n value should be the same. Suppose it is 2px, 2py, 2pz. We know all three have same energy. So according to Hund's rule, each orbital belonging to same n value should be singly occupied first. Only then pairing of electron takes place. Okay, so this is Hund's rule of maximum multiplicity. Now next let us see the electronic configuration of atoms. Electronic configuration. Now what do you mean by electronic configuration of atoms? The distribution of electrons into orbitals of an atom is called its electronic configuration. And the electronic configuration of different atoms can be represented in two ways. The first way of representing the electronic configuration is S, P, D, like this, where S, P, D are the name of the orbital or subshell. A, B, C, which are written as superscripts, are the number of electrons. Okay, A, B, C represents the number of electrons. Now, the second way of representing the electronic configuration is orbital diagram. Now, orbital diagram means the orbitals are shown in boxes. So, S orbital, we know that we have only one S orbital. So, it is shown with a box like this. Then P orbital, we know there are three P orbitals. So, the first one is Px, Py, Pz. This is S orbital, P orbital. And D orbital, we have 5 D orbitals. So, with the help of orbital diagram, we can show like this. So, this is dxy, dxz, dyz, dx square minus y square, dz square. 5 d orbitals, and the electrons will be entering into these orbitals. Okay, so this is orbital diagram. So these are the two ways of representing or writing the electronic configuration of an atom. Now, here I have written 4 columns: atomic number, symbol, then the electronic configuration represented as SPD, and last column we have the orbital diagram. So I have written here the elements from atomic number 1 to 30, and the symbol of the element is written. Now let's write the electronic configuration SPD. Now first you should know n value will indicate the period number. So you know that in period 1 in the periodic table we have only 2 elements. You can see here. This is period 1. We have 2 elements, that is hydrogen and helium. So n is equal to 1. Now for period 2 we have n is equal to 2. We have elements from atomic number 3 to 10. Now in period 3 we have elements from atomic number 11 to 18. And period 4 we have elements from atomic number 19 to atomic number 36, but we are going to write only till atomic number 30. Okay, so n value indicates the period number. N equal to 3 means period number 3. N equal to 4 means period number 4. So we are going to write the electronic configuration. Atomic number 1. So I want you to learn the atomic number and name of element from atomic number 1 to 30. Now 1 is hydrogen, and we know 1 electron in hydrogen that will be present in 1s orbital. So this is period 1. Period 1 in which n is equal to 1, and which orbital is getting filled? 1s orbital is getting filled here. Okay, that is the lowest energy orbital. So what is the configuration of hydrogen? In 1s orbital, 1 electron. So you can write the configuration as 1s1. Now helium. Helium we can write, there are 2 electrons in helium. So the configuration will be 1s2. Now the 1s orbital is completely filled. Now we move to the next period. So in the next period we have period 2, where we have n is equal to 2, and in period 2 we have 2s and 2p orbitals getting filled. Okay, because 1s is completed, only 2 electrons can be placed in one orbital. Now 2s and 2p is getting filled. So how will you write the configuration of lithium? Lithium, we have 3 electrons. So 3 electrons, first 2 electrons are in 1s2 and the third electron will go to 2s orbital. So the configuration is 1s2, 2s1. Now beryllium 4, the configuration is 1s2, 2s2. Now with this 2s is filled. Now after 2s, the next electron, that is the 5th electron, will enter into 2p orbital. So how will you write the configuration of boron? Boron atomic number 5. So the configuration is 1s2, 2s2, 2p1. If you count 2 plus 2, 4, 4 plus 1, 5 electrons. Now carbon will be 1s2, 2s2, 2p2. Nitrogen is 1s2, 2s2, 2p3. Now oxygen will be 1s2, 2s2, 2p4. Fluorine will be 1s2, 2s2, 2p5. And last we have neon, 1s2, 2s2, 2p6. And you know there are 3 p orbitals. So each orbital can accommodate 2 electrons, means total number in p orbital is 6. So with 2p6, 2p orbital gets completely filled. Okay, so our second period also gets completed with neon. Now let's try to draw the orbital diagram. Orbital diagram for hydrogen, 1s. So you need to draw only 1s orbital and 1 electron with upspin. Now helium, we have 2 electrons in 1s orbital. So 1 with upspin and 1 with downspin. Now lithium, it is 1s2, 2s1. So 1s2 is this, 2s1 will be 1 electron. Then next is 1s2, 2s2. So 1s2, 2s2. Now we have boron, 1s2, 2s2 and 2p1. Now always after drawing the diagram we should name the orbital. So this is 1s, 2s, 2p. Okay. Now next we have 1s2, 2s2, 2p2, that is for carbon. So 1s2, 2s2. Now according to Hund's rule, that electron will not be paired, 2p2. The second electron will not be paired, instead each orbital gets singly occupied. Only after that pairing takes place. Now for nitrogen we have 1s2, 2s2, 2p3. Now oxygen we have 1s2, 2s2, 2p4. 1s2, 2s2, 1, 2, 3. Now the fourth electron will start pairing. Okay. Now next after oxygen, fluorine. Fluorine we have 1s2, 2s2, 2p5. So 1s2, 2s2, 1, 2, 3, 4, 5. Now last we have neon, in which all the 2p orbital gets completely filled. 2, 3, 4, 5, 6. So this is of neon. Now the second period is over. Now starts our third period from atomic number 11. That is sodium. So this is our period 3 with n is equal to 3, and in this period we have 3s and 3p orbital getting filled. 3s, 3p orbitals are getting filled and not 3d. 3d will be filled only in fourth period. Okay, because we know when we write the increasing order of energies, 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d. So only after 4s gets filled, 3d will get filled, which means 3d orbitals are filled in which period? 4th period. Now let's see 3s, 3p orbital, sodium. Sodium atomic number 11. Now it's not possible to write always from 1s orbital. So what we do is, you can see here, neon is a noble gas. So 1s2, 2s2, 2p6 is completed. So instead of writing for sodium, 6, 7, 8, 9, 10 electrons are present. Now we have to add one more electron to sodium. So instead of writing from 1s, what we do is, we write the configuration like this, neon in square bracket. Now we know the configuration of neon, 1s2, 2s2, 2p6. Now next electron will enter into 3s orbital in sodium. So we write as neon 3s1. Okay, and we call this neon written in square bracket as core electron. So we can show the core electron with the noble gas. That is the completely filled orbital, core electron. And the electrons written outside this bracket, that is the electron added to the next highest principal quantum number, is called the valence electron. So if you look at this neon 3s1, I can say the number of valence electron in sodium metal is 1 because it is 3s1. Now here magnesium, again I can write neon 3s2 because 3s can accommodate one more electron. So 3s2. So neon is the core electron and 3s2 is the valence electron present in magnesium. And you know magnesium has 2 valence electrons. Look here. Now aluminium. Now 3s is completely filled, which means next we have to move to 3p orbital. So what will be the configuration of aluminium? Neon 3s2 3p1. And you know aluminium is in group number 13. It has 3 valence electron. Look here, 2 plus 1, 3. Okay. Now next silicon. Silicon we have neon 3s2 3p2. Now 15 is phosphorus. So again neon 3s2 3p3. Sulfur neon 3s2 3p4. Chlorine neon 3s2 3p5, and with argon we complete 3p orbital, neon 3s2 3p6. Okay, so when you draw the orbital diagram, you just have to draw the outer orbital. So if it is magnesium, you need to draw only the 3s2 orbital and name it as 3s, because we know before this 3s we have 1s, 2s, 2p completely filled. Now if you are to draw the diagram for aluminium, you can draw 3s2 and 3p1. So if you look at the orbital diagram, you know there is only 1 electron in p and 2 in 3s. So total valence electron is 3. Okay, so these are the core electrons, and the electrons written outside the bracket, they are the valence electrons. Now our period number 3 is over. Now we move on to period number 4. Period number 4 we have here, starts with atomic number 19, period 4, where we have n is equal to 4, and in period 4 we have 4s and 3d orbital getting filled. Okay, so first 4s orbital, then 3d. So let's try the electronic configuration of potassium. Potassium takes the configuration. Now argon has the configuration 3s2 3p6, neon 3s2 3p6. So again next period, now 4th period, when you write, we write the core electrons as of argon. So we have argon. Now after 3p, 4s1. So we have 19 electrons in potassium, out of which 18 electrons are the core electrons, that is of argon. Now the 1 electron will add to 4s, and the number of valence electron in potassium is 1. Now calcium, 1 more electron added, so argon 4s2. Now from atomic number 21 onwards, we have the 3d orbital getting filled, and they are called transition elements. So transition elements are elements whose 3D orbital gets filled. Okay, so after 4s we know 3D orbitals, and you know 3D orbital, d orbital, we have 5 d orbitals, so 5 into 2, 10 electrons can be placed. So how many elements will be there in that 3D? 10 elements. Now I am going to write the electronic configuration of these elements. Scandium will be argon. Now 3D is the inner d orbital. You will learn because it is coming, inner d orbital means d orbital, after d comes 4s. So that you will learn in higher classes, 12th standard. So now I am going to write argon 3d1 4s2. Okay. Now next in titaniums, this is scandium, this is titanium. The configuration is argon 3d2 4s2. Vanadium, argon 3d3 4s2. Chromium, now actually it should be 3d4, but this chromium takes exceptional configuration. The reason for that I will tell after writing all the electronic configuration. Now chromium takes argon 3d5 4s1. This configuration you have to be very careful. Now manganese take argon 3d5 4s2. Iron takes argon 3d6 4s2. Cobalt is argon 3d7 4s2. Nickel is argon 3d8 4s2. Now next we have an exceptional configuration for copper. Copper takes the configuration argon 3d10 4s1, and zinc takes argon 3d10 4s2. So in this case you can see two exceptional configuration, that is chromium and copper. Chromium, instead of taking 3d4 4s2, it took 3d5 4s1, and copper, instead of taking 3d9 4s2, it took 3d10 4s1. Okay, so 10 elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, whose 3D orbital gets completely filled. Okay, now let's see the reason for this exceptional configuration of chromium and copper. The reason is due to they want to get extra stability, and if I write, I'll write it again. Chromium, the configuration is argon 3d5 4s1. Now if we draw the orbital diagram, this is 3d5 and this is 4s. You can see all the orbitals 3d and 4s are singly occupied or half filled. So it is said that if an element has half filled orbital, it has got some extra stability. So chromium takes this configuration, there is argon 3d5 4s1, to get extra stability due to half filled orbital. Same way, let's see for copper. The configuration of copper is argon 3d10 4s1. Now when we draw 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4s1. This is 3d10 4s1. You can see in d orbital, 3d orbital, all the electrons are paired, which means completely filled d orbital. So we can say half filled and completely filled orbitals have extra stability. So to get this extra stability, chromium and copper takes this configuration. Okay, so chromium gets its stability due to half filled orbitals and copper gets its stability due to completely filled d orbital. Now, what is the reason for this extra stability of half filled and completely filled? They are giving two reasons. The first reason is due to symmetrical distribution of electrons in half filled and completely filled orbital. there is a symmetry in the distribution of electron. And the second reason is exchange energy. That's the second reason. Exchange energy. Now, exchange energy means the electron in degenerate orbitals can exchange their positions. Okay, degenerate means same energy orbitals. They have a tendency to exchange their positions and an energy is released. And that energy released is called exchange energy. And the number of exchanges that can take place is maximum when the orbital is exactly half filled or completely filled. So we say that as a result they have maximum exchange energy and maximum stability. So these are the two reasons for the extra stability of half filled and completely filled orbitals. Thank you.